Welcome, everybody. So today we have John Lagacé. I suspect most of you know John by now. He's King's College, and today he'll speak about spectral inequalities on manifolds with bounded sectional curvature.
Thanks, Simon, for the introduction. And as indeed is written here, I'll talk about these spectral inequalities. And this is joint work recently on the archive with Alex de Laporte in Paris-Saclay and Marc Rouverol, who's currently in Bielefeld. So, of course, if I want to talk to you about spectral inequalities, I should first of all tell you in what setting am I trying to find spectral inequalities, because I have to say that when I started working on this area, I thought, aren't all the inequalities we're working on spectral inequalities in some form or another? But apparently, some specific ones get to hold that name. And so, in the setting where I will be working, MG will be some Riemannian manifold, and omega will be a subset of M. And I will say that M, G, and omega support the spectral inequality. If for all, if there exists a C greater than 0, such that for all u in L2 of the manifold, we have the following inequality. The norm of u in L2 of M is controlled by an exponential, the norm of pi lambda of u times the norm of u in L2 of omega, where here this p lambda is the spectral projector for the Laplacian on the interval 0 to capital lambda. Okay, so a few remarks. Well, first of all, taking square root of the Laplacian here gives me lambda to some linear power here. I don't remember if in some of the talks we've seen already during this program on the spectral inequality, either by Michela or by Eugenia in the beginning of the semester. Maybe this was for the Laplacian and the square root of lambda or something, but this is, of course, the same thing. Also, you'll often see this kind of statements written as either pi lambda of u on both sides, or the statement of the definition being said, okay, for all u in the range of this spectral projector. Of course, if I write it like this, it's equivalent. And I take spectral projector in the situation, especially because I will also care about the situation where the spectrum might not be discrete. Sorry about this. Yeah, I still care about the situation where the spectrum might not be discrete, where this will still hold. And how should you think about a result of this type?
You don't want to project it on the spectrum.
It doesn't matter. What I'm saying is that it's equivalent whether I put it or not, right? Because if it's true with the spectral projector on the right, it's true for this. But if it's true for every u, it's in fact also true for u's in this range of the spectral projector on the right, so which will imply this result. So you really don't have, it doesn't, it's a convention whether to put it or not on the right. Okay, and how to think of this, but if it makes you more comfortable, we can also do this. It's the same thing. How you should think of this result is that if you have some function in L2 whose energy is bounded in some sense, then if I know its value on the set omega, if I know its L2 norm on the set omega, then the L2 norm on M cannot be too large. So we will often see these kind of results referred to as propagation of smallness in some way. And the reason why it should, of course, so and of course these kind of results will feel interesting when omega is a small set, because of course if omega is a large set, well, you would certainly expect to see most of the L2 norm to be on any sort of large set. And the reason why we see this dependence on lambda here is that if I think of this as, if I think of omega as a very small set, then of course if U is very oscillating, which means that it has large energy, then it should be able to somehow avoid a small set where U is large, whereas if it doesn't oscillate a lot, it shouldn't be able to do that. And so the goal here, or the goal in general here, obtain a C that is, quote unquote, as uniform as possible so that the spectral inequality ends. And the reason why I would do this is in part because of what are the applications of such a spectral inequality, which are following the tradition of Eugenia 3 weeks ago and Michaela last week. I will not dwell on the applications too much, but the applications are in general to control theory, for example, of the heat equation associated with this Laplacian, and being able to choose some sort of source term that would bring the solution to zero in the shortest amount of time possible, or for the lowest cost possible. And basically you want to be able to do that in control theory, somehow knowing how much you will spend regardless of the starting data of your problem, and somehow this C here will be in these control problem equivalent to some sort of cost. If we can't.
It's a very weak restriction inequality. If you decide that U is an eigenfunction, that's allowed, right?
Yeah.
Then this would say that the L2 norm restricted to this thin subset omega is not too small.
Yeah.
Ideally, you would take C equals 0.
Ideally, you would take C equals 0, but I mean, that's too much to ask for. Sure. I'm sure there's some times where it's not too much to ask for. I think in particular, if you follow the works of Dyatlov and Jin on compact manifolds, you can take C equals 0, I think. But our goal is to look at not compact manifolds here. Torus. Anyways, I'll have to think more about the specifics of that, but what I am sure is that in the context I'm looking at now, we won't be able to take C equal to 0.
You can't have this with C if omega doesn't have the full measure of that.
Right, okay. So on the flat torus,
Yes. If you
this
take
is okay. Look at the eigen.
I mean, it won't be C. It won't be C equals the C might come on the one here and still depend on the properties of small omega. What I meant was more independent of lambda in the constant that's on the left hand side. That's how I understood taking c equals 0 in this case. Yeah. That was more my. No, of course it cannot be c equals 0 for all sets omega.
There's a constant.
Yeah. Okay. Anyways, now a first property that's very quickly seen to be somewhat necessary on the set small omega is that it somehow samples enough of your manifold. So I will say that so for epsilon and r greater than 0, omega is said to be epsilon r thick if for all x in the manifold, the volume of the ball at x of radius r intersection with omega is larger or equal than the volume, than epsilon times the volume of this. Okay. So basically, the statement is just saying that in omega will be epsilon r thick if wherever I look on my manifold, I look at a ball of radius r around that point, and my omega is present in at least an epsilon ratio of that ball. And in a way, I guess it shouldn't be too surprising that if I want an inequality of this type, for every omega, I need to only look at omegas that are somewhat present everywhere on my manifold. And it is what I will write as a fact. C has to depend on epsilon and r. Yeah, I think you can make it in many cases depend on the ratio between epsilon and r, but at any rate, these are parameters that should appear in your quantity. I mean, of course.
So what do you want omega to be? Omega is fat or omega is thin?
I want to think as omega thin.
Like a closed geodesic is okay?
No, because a closed geodesic, in a small neighborhood of some closed, omega needs to be somewhat dense in everywhere on my. It needs to sample a bit everywhere on my manifold. And the smaller I take epsilon, the worse my constant's going to be. But I don't want it to depend on omega in other ways than this sort of at what rate do I sample everywhere on my manifold.
Particular kind of set in mind?
Something that's as thin as possible. So I mean,
For me, it's a closed geodesic, but this definitely doesn't satisfy this, as you said.
take a Poisson point process and take small neighborhoods of all the points that you have decided. That would be a set that I would be interested in. Okay. Now, in various contexts, omega epsilon r thick implies that m g omega supports a spectral inequality in some situations. Okay, and I'll just mention a few now. So in flat space, that's the result of Michela and Veselic on compact manifolds without too much regularity assumptions. That's Burke and Moyano. Or if M is hyperbolic, that would be by Delaporte and Rouverol. And in these, of course, on compact manifold, this thickness assumption is satisfied for every, say, omega of positive volume. But the result would still depend on the parameter epsilon and r. Flat space, that's the only thing it will depend on. Hyperbolic, you might have a dependence on, okay, if you decide to normalize rather than curvature equals -1 to curvature equals minus something else, but constant. The C might depend on that choice of curvature. And the theorem that we prove is, so let kappa and r be greater than 0, epsilon in 0, 1, and d some natural number. There exists C greater than 0 such that for all mg of dimension d, with the norm of the sectional curvature in L infinity smaller or equal than kappa, and omega epsilon r thick, and u in L2 of m, the norm of p lambda u in L2 of m is smaller or equal than e to the c lambda plus 1, norm of u in L2 of small omega. Okay, so what we obtain is that this constant c depends only on dimension, epsilon, r, and the norm of the sectional curvature on the manifold. Now, what before telling you a bit about how this is proven, let me just mention what would be the ideal result. The ideal result would be to replace this condition on the sectional curvature by instead a condition on the Ricci curvature. And I would like that condition to be, in fact, that the Ricci curvature is just bounded below rather than a two-sided condition. And I will try, when I give you a sketch of the proof today, of telling you where specifically we use that it's the sectional curvature rather than Ricci. And in one case where we use really that it's two-sided, so that if you have ideas how to simplify those steps, you would be able to strengthen this result. The other thing that I want to mention, and this is crucial here, is that a geometric quantity that is conspicuous by its absence is the injectivity radius. Okay? This C does not depend on the injectivity radius, and normally for these kind of bounds, that would be a geometric quantity that we would expect to appear in the bound. We could state this theorem if I could replace sectional by Ricci, still above and below, and add injectivity radius bounded away from 0, and I would get the same result with C depending only. So sectional allows us to remove the injectivity radius from the conditions. And I'll try again. I'll try to make it precise in the sketch of the proof where this is really necessary. Are there questions at this point? It's trackable down if the only reason why we don't do it, I mean, we actually do it for most of the paper, and at some point we have to use a quantitative unique continuation result from Lagudov and Malinikova, in which it's in principle tractable in that paper, but we didn't. But that's up to how specifically it depends on the geometry there. Yes. Because every other way in which it depends on the constant is basically a dependence on some doubling inequalities that depend only on the curvature. So and in a very, very explicit way. So that part is somehow fine. Oops. Any other questions at this point while I erase the where is? Ah. All right. Yes. Huh? No, as I mentioned earlier, it's equivalent to not have it.
That would be a consequence of a claim. Whether it's true or not, I'm not sure.
No, but it says for all u and L2 of m, there are of course u and L2 of m that vanish in only.
Yeah, this is true.
Yeah, sure. No, that is right. This. Yeah. No, this is of course correct. The sort of equivalence I had in mind is not. This is something that needs to be there. You are correct. All right. So the proof of the statement can be split into 5 steps, or I mean, you might count them as 2 steps, and one is one part 1 to 4, because that one is really 4 times the same step, slightly different way. And so let me start with step 5. Which is to use quantitative unique continuation theorem, which I will abbreviate as QUC for the rest of this talk, on the spectral projector. To get the spectral inequality. And so let me state what is this quantitative unique continuation theorem that we use. Take d greater or equal than 2, kappa r epsilon and t greater than 0. Then there exists c and beta greater than 0, such that for all mg with dimension of m equal to d, and the norm of the sectional curvature smaller than kappa, and all u from M to R, phi from M cross minus tt to R, solving Laplacian. So this expression that I write here is the Laplacian, if this phi is harmonic in M times minus tt. Phi at t is 0 is 0. The normal derivative of phi at t is 0 is u. And omega in M then is epsilon r thick. Then the norm of u in L2 of M is smaller or equal than C, the norm of u in L2 of omega to the power beta, the norm of phi in L2 of M times minus t p to the 1 minus beta. And so the picture that you want to have in mind here, so we use this trick that we've seen a few times during this program at this point of lifting to a product space and looking at harmonic functions on this larger space there. And in this, basically this is M times minus t, where this direction is M and this direction is minus t. And I have this slice here at that's t equals 0, and I have some small set omega inside here. And basically my claim is that if I have my phi that's harmonic on this whole M times minus t, and it vanishes on the t equals 0 slice, and I know its normal derivative on its t equals 0 slice, then I can control the norm of this normal derivative on the whole of the slice by the norm of u on this normal derivative on the smaller set times the norm of the whole harmonic function on the whole product space. So let's see briefly how this will allow me to get the result by applying this to the spectral projector. So I'll define phi lambda of xt. That will be sinh of t times p lambda u, which is the integral from 0 to lambda of sinh lambda t over lambda d mu of lambda u of x. Okay, so this is just I defined this via the functional calculus. Now phi lambda of xt satisfies I have defined it specifically as the function that will satisfy my boundary conditions here, or as a function that satisfies this. And so this means now that the norm of p lambda u in L2 of m, because it satisfies this with u being p lambda u in L2 of m, will be smaller or equal than some constant norm of p lambda u in L2 of omega to the beta norm of phi lambda to the 1 minus beta in L2 of m times minus t. And now this thing here, I can bound by phi lambda in L2 is bounded by the supremum over t in minus t lambda in 0 lambda of this quantity times the norm of p lambda u in L2 of m. That's an inequality that follows from the functional calculus. And if this here, that's smaller or equal than e to the lambda t. And if I plug this into this inequality and rearrange, I get the statement of the theorem that is down. No. That I erased. Is there? Ah, yeah, that is there. I get this theorem by rearranging. In fact, it gives me e to the lambda t over beta in this times some constant in front, and that constant can be absorbed in the e c plus 1. Okay. So if I have this theorem, then I'm done. Now, you might have noticed that this said step 5, and I guess step 1 to 4 is getting this theorem. Now, let me state the theorem that we have and that we use as a starting point, and I'll highlight what are the things missing. So there's this theorem from Logunov and Malnikova in 18 that says, so we have omega in Rd bounded domain. A from omega to Rd times d, a family of symmetric matrices uniformly elliptic Lipschitz coefficients phi a solution of div A grad phi is 0, and omega compactly contained in some E, compactly contained in some big omega with the d minus 1 Hausdorff measure of small omega greater than epsilon, the distance from omega, well, from E, I guess, to the boundary of omega greater than some delta. Then there exists, take another color for a second, C greater than 0, such that the gradient of phi is in L infinity of E is smaller or equal than C times the gradient of phi in L infinity of omega to the power beta times the norm of the gradient of phi in L infinity of the big omega to the 1 minus beta. Okay, so what is this statement saying? So I use a different color for a reason. This C greater than 0, what does it depend on? On this delta here, this epsilon here, this D that has to actually be greater or equal than 3 here. It depends on this omega here, this ellipticity property, and these Lipschitz coefficients, but not on who specifically omega is, small omega or small e, apart from through these properties of them. And also not on who A is apart from on those two properties. So what is missing if I want to get this result and I know this result? Well,
sorry, what do you mean it depends on the fact that it's coefficients but not on A? You mean that you impose some sort of uniform?
Yeah. It depends on the Lipschitz. Yeah, I guess rather than put coefficients, it depends on the Lipschitz character of the coefficients, and not on anything that's not the Lipschitz coefficients, the Lipschitz character of these coefficients. And so, part of our job here will be to bring this result that's for RD into a result on manifolds. We'll have to somehow remove this dependence on this set omega here and manage to work with either the same omega all across or remove this dependence. We'll have to ensure that, so that this Lipschitz character is not only something that depends on the Lipschitz constant, but also on the size of sets on which this Lipschitz constant is measured. So that's something that we'll have to control. Okay, this distance will not be a problem. This is really, in a way, our thickness property. And also this result, somehow we apply it in the situation that we are a codimension 1 object in this product. So somehow the context of this is the right one for us. By the way, d greater or equals than 3 here. I mean, we're starting on some m, at least a surface that we take a product of. So this m times minus tt will be of dimension 3 at least here. Okay, so our goal is to go from this theorem to that one. And the scheme of the proof for that looks like the following thing. So global quantitative unique continuation on M, and I'll write, when I write uniform here, I mean uniform if I fix the dimension and norm on the curvature. And this will be implied by uniform quantitative unique continuation on Bx r, any x in M, and R is the thickness scale. This will be implied by uniform QC on BXR R small enough in terms of B and kappa, but not, I mean, if it has to depend on other quantities, that's not good. This will be uniform QC in a chart. And this will be this result here. And so that's, of course, step 4, step 3, step 2, step 1. Okay. All right. Any questions at this point? All right, let me do so quickly. Step 4 and step 3. They consist in covering arguments using the fact that the norm of the sectional curvature smaller or equal than kappa gives control on the multiplicity of intersection plus on the number of balls of radius r required to cover balls of radius big R. Okay, so I won't go into the exact details of how this is done, but this is somewhat standard as part of the argument. Step 1. So we go from L infinity to L2 estimates via Eldar, Chebyshev, and elliptic estimates. Okay, and which one depending on which term in the inequality I'm looking at. But the important thing is that in going from this to quantitative unique continuation in a chart, one of the things that I'm using here is that my metric will have uniformly Lipschitz coefficients, because the Laplace-Beltrami operator in a chart is essentially a divergence form equation with the coefficients of the coefficients A being essentially the metric there. And so I will need to use there So input G is uniformly Lipschitz, and or depending on kappa ultimately. Okay, and here I need an injectivity radius bound. Okay, because as I was saying, when I say that this depends on the Lipschitz character of my coefficients, part of the Lipschitz character is on how far I need to open up my manifold to be able to observe this Lipschitzness. Okay, and now I want to do step 2, and part of step 2 will include the step 1.5 to show that I can input the correct data in my step 1. Okay, and so step 2, the enemy is something that looks like this. Okay, that I will have, or this, or maybe there's not, maybe it's just this picture. Maybe this is a cospath infinity, or it's a sequence of things where I pinch something, or this is a cospath infinity. So these are the enemies. And while my global injectivity radius in something like this is 0, at any points in the interior of my manifold, the injectivity radius is not 0 at that point. And so what I'll want to do is I'll want to use coordinates, if this is a point P, that come from the tangent space at P in here, where I will take a ball here, and this ball here will correspond to some set here that I will send via, actually the arrow goes in that direction here. I will do this via the exponential map. And now this exponential map will wrap many times around this. Well, maybe if I go in this direction, it doesn't wrap. If I go in this direction, it wraps many times around. And so what do I know? So there's a theorem of Rauch that tells us that in a ball of radius, say c dimension over root kappa, I think you can actually remove the dimension bound here. The map that brings the metric that comes back from this is well defined. Every point has injectivity radius at least some other constant, maybe over root kappa as well. And so that's the first thing that I need to know. The second thing that I need to know is there exists RH on, so that I can define harmonic coordinates on B in TPM 0 RH, and RH depends only on kappa and the injectivity radius, but this is not the injectivity radius of M. This is the injectivity radius of TPM, where in fact that injectivity radius is controlled by the sectional curvature of M. And so this is just based on kappa. And why do I want harmonic coordinates? Is that harmonic coordinates are have the best regularity of the metric. So regularity of the metric is something that you observe in coordinates. And harmonic coordinates are the correct choice for having the best regularity. You have examples, for example, where the geodesic coordinates, which is what we would want to use with the exponential map, have strictly lower regularity. And by some elliptic regularity results, we can show that the metric on this ball has Lipschitz coefficients where you depend only, again, on kappa. In fact, here we could replace sectional with Ricci bounded on both sides, and we will get these same bounds. Okay, so here G is uniformly Lipschitz. And the last point is that I can use some volume doubling argument to show that every x in the ball of around p of radius r has RH has more or less the same number of pre-images by this map exponential of p. Okay, so basically the way that I will wrap around some sort of thin cylinder will lead me to have up to uniform constants above and below that will depend on kappa, of course. I will always have more or less the same number of pre-images, so that when I use my theorem in charts to get my quantitative unique continuation in the tangent space, I can bring this down to the manifold below by the fact that I don't stretch the result by more or less depending on where I am in this ball of radius r. So in the end, I apply the result in charts on the tangent space, which allows me to bring it down in balls of small enough radius on the manifold of radius, the harmonic radius of the tangent space, which allows me to bring in large balls on the manifold, which allows me to get the global quantitative unique continuation, which gives me the spectral inequality, and that's it.
John, for a lovely talk. Do we have questions?
I don't like this tradition of not giving applications, so let's stop it now. Can you give an application?
I mean, I should have thought about this and prepared the application more, but
Immediately,
no, but okay.
semester. Something which has no application is less of interest to people or not exactly in the subject. Like,
Yeah.
number theorems.
So, I mean, the application might not be of more interest to number theorists, but I will still give it. Sorry for for this, but there's a question in control theory where if so I want to solve the heat equation Laplacian of u. I will make a sign mistake if I don't think if I do this on the board in front of you, but bear with me on the sign mistake, which is equal to some function f, and u at t equals 0 is equal to say some function phi. And the question is, given a time t greater than 0, can I choose f, or can 1, I'm not alone in this, choose f so that u at time t is 0. So this is called null controllability. And I mean, from sort of homogeneity perspectives, I guess you can then choose also an f to send you to some other functions at the end. But now the question is how large do I need to make this f, and on this f might be actually only supported on some small set omega. And basically how large I need to make this f on the small set omega and how big this omega needs to be is controlled exactly in terms of the same constant that we have for the other. I mean, this is what I'm not ready to do is exactly what's the relation between them, but they depend on the same geometric quantities. So this null controllability here it has the same geometric dependence on a starting manifold. Similarly, I mean, this also can be reframed in terms of what's called observability of the heat equation. If I see a solution large enough on some set, is this large enough everywhere else, and this kind of things. So that would be the application that people have dropped on in the talks.
Other questions? I think there's one.
So then upper bound and Ricci curvature, what kind of geometric information it gives you? Because you don't have any comparison.
So what it gives you is in the elliptic regularity. So how do you prove the fact that harmonic coordinates give you some regularity? Is that in harmonic coordinates you have that both Ricci and sectional curvature are represented by elliptic nonlinear operators of the metric, and with various strength of ellipticity assumptions on there. Upper bound, I mean, two-sided bounds on Ricci in this. So bounds on this means or I mean Lipschitz, depending on how you want to notate it, gives bounds on G in the Lipschitz norm, whereas Ricci greater than say, minus C, this gives norm of G in C0 alpha for all alpha smaller than 1, but crucially not in C01. Now, what is I mean, part of a further investigation is in the result of Logunov and Malinikova, it is probable that we can reduce the assumptions on the metric from Lipschitz to some space that lives between every C0 alpha and Lipschitz. what we know is that we cannot reduce it to C0 alpha for all alpha. This makes it not true, but there's probably some bit of space in between that is the optimal space for this result to hold. What is also true is that the Ricci greater than minus C doesn't really give you C0 alpha. It gives you some Bizov space that sits between all C0 alpha and C01 as the optimal target space. And now the question that we need to ask is this the situation, or is... So basically, do the assumptions that are required for this result to hold, do they fall below the regularity that this guarantees us, or do we have a gap and then we really need to do something different for it to make it work? But that will require some quite careful regularity theory investigations. Yeah.
So am I just about this uniform Lipschitz?
Mhm.
Am I right in understanding that here the issue is the uniformity, not the Lipschitz nature, right?
Well, it's the uniformity of the Lipschitzness.
Is uniformity of the Lipschitz constant with respect to
In the sense that if I fix kappa, this Lipschitzness character is the same for every x on every m wherever. I mean, if I change kappa, I might get worse estimates on this.
It's just so the uniformity is the key, not the regularity, because in a way you're always guaranteed to be Lipschitz. No?
It's the uniformity of the Lipschitz norm. No, it's always Lipschitz of something, but it's the same for everybody is the point.
Further quick questions? Otherwise, we postpone it to. Let's thank Jan again.